In complex industrial systems, failure rarely comes without warning. But too often, the early signs go unnoticed, lost in noise, missed by thresholds, or hidden behind normal-looking data. What if we could compare every real-time measurement against its expected behavior, continuously and at scale? This is the power of simulator-driven condition monitoring. No one saw it coming. At this moment, the plant was losing production. A compressor tripped. Downtime started. No alarms gave advance notice. It wasn't just a trip, it was a breakdown in detection. Beyond the failure, here's what it meant. Over a day of lost output, $250,000 in revenue losses, and emergency maintenance that cost 3 times more than a planned stop. All of it avoidable with earlier insight. But the warning signs were already there. A month earlier, a small but consistent deviation started. The real plant was drifting. However, no thresholds were crossed, and no one noticed the drifting temperature because the drift was so slow. Conventional monitoring didn't catch it. What if we had a tool that flagged growing mismatches before they turned critical? An ideal system wouldn't wait for an alarm. It would alert the user as soon as the drift began, triggering an observation phase and enabling a proactive decision, like starting the standby compressor before failure occurred. In many plants today, our monitoring systems are still reactive. Alarms go off only after something goes wrong, leaving no time to prevent damage or disruption. And while we rely heavily on field sensors, we rarely know when they start to drift. This slow degradation doesn't trigger alarms, but it steadily erodes performance and reliability. Add to that the problem of siloed systems. Maintenance data, process trends, and operator observations often live in separate tools, making it difficult to see the full picture. The reality is modern plants are too complex for static thresholds and disconnected monitoring. Interactions between equipment and systems create subtle patterns, and without the right tools, those patterns go unnoticed. By the time a deviation becomes obvious, it's often too late to act proactively. We've missed the opportunity to correct course early, and we're left reacting instead of preventing. This is where our innovation comes in. Instead of waiting for alarms, we continuously compare live plant data with a high-fidelity simulator, essentially a digital reference for how the system should behave. Every measurement is tracked against its modeled equivalent. We calculate the root mean square deviation over time, a single, explainable metric that shows how far reality is drifting from expectation. When the RMS trend begins to rise, we know something's off. No need to define every fault mode in advance. The system flags deviation and surfaces it, guiding early intervention. It's a simple idea, but incredibly powerful in practice. And it's built entirely on tools we already use. Here's how it could have worked in the compressor case. In this case, it was the derivative of the RMS deviation that gave the earliest warning. As the temperature began to rise, still well within normal operating limits, the derivative detected a sudden change in system behavior, triggering an early alarm. This initiated an observation phase. The deviation itself remained small, but the rate of change was increasing, a clear sign that something was starting to drift. The system continued monitoring both the RMS value and its derivative. RMS deviation is excellent for catching gradual drifts over time, slow but persistent deviations from expected behavior. RMS derivative is ideal for capturing sudden changes, when a variable starts shifting more quickly, even before absolute values trigger conventional alarms. With these insights, the operator would have been alerted early, monitored the trend, and proactively decided to bring on the standby compressor before the situation became critical. This is exactly what we mean by model-driven condition monitoring. Early signals, structured insight, smarter, faster decisions. And this is just the beginning. The system as it stands today is already powerful, providing real-time comparison, deviation tracking, and early warning based on simulation models. But looking forward, there are exciting opportunities to make it even smarter. Machine learning could be used to automatically recognize deviation patterns across thousands of signals, identifying hidden risks even faster. AI-driven trend analysis could recommend optimal observation periods, predict fault progression, and even suggest corrective actions before problems escalate. Self-learning models could gradually fine-tune alarm thresholds and sensitivity based on plant behavior, improving both robustness and accuracy over time. In other words, today, we're using the model as a live reference. Tomorrow, the system itself could learn and evolve alongside the plant. This is not just a new feature. It's the start of a journey toward truly predictive and intelligent operations. This is illustrating what the operator or engineer would see. A dashboard within Cogniquant simulation with a clear overview of where the simulator and plant are in sync and where they are drifting. Each unit or tag has a live RMS trend, color-coded status, and time filters to zoom in on change. Instead of hunting through alarms, they get a prioritized list of where to look and why. This isn't a one-off solution. It's a generic, scalable capability. As long as you have a simulator that describes expected behavior, you can use it for condition monitoring. Whether it's a small model around a single valve, a subsystem like a compressor station, or a full plant simulation, it works. The tool doesn't care about the model size. It just compares field behavior to model behavior in real time. For example, a heat exchanger showing gradual loss of performance before fouling. A separator with level control issues that start to drift days before alarms. A valve with sticking behavior causing subtle mismatches in flow. Anywhere you have a model, you now also have a condition monitor. Early detection means fewer breakdowns, less unplanned downtime, and smoother operations. By catching deviations before they escalate, we prevent both production loss and safety risks. This system also helps reduce maintenance costs. We avoid emergency repairs and shift toward condition-based intervention, using the simulator as a live reference. But most importantly, it brings teams together. Operators, engineers, and maintenance staff all get a shared view of system health. No silos, no guesswork, just informed, proactive decisions. Start using your simulator as a live condition monitoring engine. Your simulator already knows how the system should behave. Let's use that knowledge, not just to simulate, but to protect, predict, and provide real-time insight. Let's unlock the full value of the digital twin.